This past weekend, we held the NANOG Hackathon, which we hold the weekend before NANOG conferences. It is organized by the program committee, and its goal is to promote NANOG's educational mission. We aim to share knowledge, to enable professional development, and to develop the next generation of networking professionals. We've experimented with a number of different formats over the years. We've provided exercises to complete an achievement of a goal. There have been participant-driven projects centered on a theme, and we've had entirely open-ended participant-driven projects. Participants choose to work individually or self-organize into groups. And this time we had a theme, which was configuration modeling. Modeling is foundational to configuration automation systems. At any level of complexity, from intent-based networking or network graph systems to a single peer on a single device, robust models are necessary in order to provide guarantees of correctness on how a network is configured. To support heterogeneous networks, vendor-independent abstract models must be used. As our first participant-driven project theme in quite some time, we thought it would be fitting to pay homage to the very first NANOG Hackathon, which took place nearly 5 years ago at NANOG 67 in Chicago. The theme then was Source of Truth. We've taken that foundational theme and encouraged participants to advance it. Since that inaugural hackathon at NANOG 67, we've held 11 more. This is our second virtual one. Hackers worked all weekend, but finished ahead of the Super Bowl kickoff. Like last time, we have participants from outside of North America. Tony Yannick Colombo from South Africa and his NANOG 80 hackathon partner, Barry Jones-Cook, have been working together since the last hackathon. You can read about them in a recent NANOG story. This time they were joined by Jose Montero Martin of Spain and Pete Wykowski and Nate Sales of the US. Of special note, Nate Sales is currently a high school student and will be giving a talk on building an open source Anycast CDN. They were among a small but engaged and enthusiastic group of participants who worked together on 5 projects in total, either on our theme or on a topic of their choosing. The projects included a NetBlocks Yang plugin, configuration push via netconf, and virtual infrastructure on Vagrant on Windows. Today you'll be seeing presentations on 2 projects. Zoe Blevins will be presenting her work on config automation with OpenConfig, and she'll be followed by Tony, Barry, Jose, Pete, and Nate on telemetry lab automation.
All right, hi everyone, my name is Zoe Blevins. I am a senior software engineer at Netflix OpenConnect, with a focus on creating distributed systems and platforms to support our network and systems infrastructure. And today I'm here to talk to you guys about a hack I did to play around with config automation using OpenConfig Yang models and GNMI. And so just to start, I'm gonna go over a little bit of terminology. So OpenConfig, I went ahead and pulled this description straight from their website. I don't want to put any words in their mouth, so I'm going to read it as it is. But OpenConfig is an informal working group of network operators sharing the goal of moving our networks toward a more dynamic, programmable infrastructure by adopting software-defined networking principles such as declarative configuration and model-driven management and operations. One of the things the OpenConfig group does is produce Yang models that are based around modeling individual network elements and kind of driving us toward that intent-based kind of network modeling. And so Yang itself is just a data modeling language. It was created for the purpose of modeling network state and configuration. There are also 2 protocols I'm going to talk about here, GNMI and GNOI. GNMI is just a gRPC interface used to send and receive OpenConfig data to and from a router. GNOI is more operational based, so it's used for kicking off operational tasks, things like initiating pings, clearing interface counters, rebooting a router, operational things that aren't really tied to the network model or the network configuration. And so a lot of what I'll be talking about today is taking those OpenConfig Yang models, populating them with data, and sending that data to the router for the purpose of configuring it. So I went into this hack with 2 main goals. My goal was to fully configure a lab network using only OpenConfig and GNMI, no hand editing, no other SSH-based tools, just purely GNMI. And then also to perform state validation using GNMI after making those configuration changes. And so just a real quick look at my lab environment. I've got a management switch that's there just to connect my Linux desktop directly into all the routers so I could perform management tasks such as SSH and GNMI connections. And then I have two core routers that are in BGP AS64512, and then two top-of-rack routers that are in BGP 64513 and 64514 respectively. Those both have an Ubuntu host hanging off of them and a locally configured VLAN on the top of rack. And all of the routers are running CEOS, just containerized version of Arista's EOS. And this is all kind of accomplished with GNS3. So I want to talk first about the configuration, kind of individual configuration items I was able to achieve with OpenConfig. First being creating point-to-point links between two devices. This is bringing the interface up and applying an IP address. I was able to initialize BGP with a given ASN, redistribute connected routes into BGP, add BGP neighbors, create an SVI, and modify VLAN settings on a port. Put a little asterisk there for the SVI. Unfortunately, there was a bug in the version of EOS that my lab was running. And so while the SVI does get created, it gets created with an MTU of 0, which puts the port in a pretty wonky state and does require a little bit of a manual tickle to get it up. So I then took those kind of individual configuration tasks and grouped them into APIs for kind of common operational tasks I envision when managing kind of a data center network. And so those three tasks are provisioning the new top of rack, adding a VLAN to a top of rack, and then editing access ports. And so the provision task creates the entry in the database for the top of rack. It creates point-to-point links to the core router, sets up BGP, all that good stuff. Adding VLAN obviously creates the SVI. Then editing access VLANs is exactly what it sounds like, just changing what the access port is, maybe doing some port descriptions, things of that nature. The backend database for the system is a really simple SQLite database. There's not a lot of thought put into the structure of the database, so please don't judge it too harshly. But for each device, we just store the host name, the management IP, and the role, and then a set of, we have a separate table for the configurations, which are keyed off of the OpenConfig path, and then store the actual JSON object that we want to send via GNMI. I chose to store each of these OpenConfig paths as individual elements rather than using the top-level trees. For me, that felt easier. I could store the individual elements, interact with those individual elements cleanly versus having to pull the whole tree out of the database, navigate the piece I want to edit, and then store it back. I'm not positive that this was the best way to go about it. This is, again, my first time playing with OpenConfig. This was just what made the most sense to me. I'd be definitely interested in hearing how other people kind of tackled that. And so just a quick look at what that database looks like. This is just output from my API. You can see here, as I mentioned, we store the host name, the role, the management IP for the device. And then we store a list of configs. I've included the Ethernet 1 config here, and you can see that we have the path, and this is the OpenConfig path for configuring, and the actual JSON structure that we send to the device. And you can see where the interface description gets set, where we unshut, setting it to enable true is kind of functionally the same as unshut. We set up our IP address here, 10.0.0.0 in this case, with a prefix length of /31. And so I want to kind of take you guys through a quick demo of using the APIs that I created. And so part of setting up the lab, my API, when it comes up, it populates data for TOR 1 and for the two core routers, but it leaves TOR 2 completely unconfigured and unpopulated. And so I'm going to step you through what it looks like to fully configure TOR 2 from scratch. And so here's our initial state. You can see, if you remember from the lab diagram, Ethernet 1 on TOR 2 connected up to core router 2, port 9. Ethernet 9 on TOR 2 connected down to host 2. And then, as I mentioned, it had a VLAN configured, and it was using BGP as the routing protocol. So in this case, I've got everything defaulted. There's no configuration of those Ethernet interfaces. There's no VLAN 102 yet, and there's no BGP running. So here's a quick look at what that provision TOR API looks like. You can see the inputs here are the host name and management IP for the new device, what ASN it's going to reside in, the prefix we want to use for the point-to-point link up to the core router, and then what exact core router and port we're connecting to. That's important because this API actually configures both ends, so it will hit core router 2 and TOR 2. So assuming we've provided this data to the API and we hit submit, in a few seconds we'll have this output on the TOR. So if we look at Ethernet 1, you can now see we've got our core router 2 Ethernet 9 description there, the IP address. If I made kind of a decision that the top of rack will always have the second IP and the prefix supplied. So Ethernet 9 on core router 2 has the 10.0.1.2, and this port has the 10.0.1.3. You can also see here that it brought up BGP with the right AS number. It redistributed connected routes automatically, and it configured that core router 2 IP as the neighbor. And then we can actually look at our route here and see all the routes that we learned from Core Router 2, including 11.0.1.0/24, which is the VLAN that's running on the on TOR 1 that host 1 is connected to. And so at this point, the top of rack can connect, top of rack 2 can ping host 1. So the next step is to configure an SVI, configure that VLAN 102 that I mentioned before on the top of rack. And so in this case, we pass in the host name, again, for our top of racks. We know exactly what device we're trying to configure on. The VLAN number, we're trying to configure the prefix to apply to that VLAN and a description for it. And when we hit submit, this is what we see on the device. As I mentioned, we hit that bug with a specific version of Arista. So you can see the IP address does get created, the interface gets created, the IP address gets created, the VLAN shows up, but it's got an MTU of 0. And another funny thing here is you can see that the show and VLAN has the description, but it doesn't actually show up in the config. If I do hop on and run a no shut, it cleans everything up. The description does show up in the config and the interface works, but in its current state, due to that bug, with the MTU being 0, it's in kind of a wonky state. And then the final step is to actually put our host 2 in VLAN 102. And so this is the set access VLAN API. Again, we give it the host name of the device we're trying to modify. And then we set the port that we're trying to modify. So Ethernet 9 in this case, the access VLAN will be 102 and a description to put on the port. When we hit submit on our top of rack, we can look at port 9 now and see it's got description, host 2, it's an access VLAN 102. And so at this point, host 2 would now be able to ping host 1 across our lab network. All right, so I kind of outlined my goals at the start of the presentation. I would talk a little bit about what I was able to achieve. So I did manage to fully configure my network, my lab network, using only OpenConfig and GNMI, with the exception of having to do that no shut on the SVI to make it work. I also was able to add some verification steps in during the provision process that do OpenConfig GNMI, or do gets against the OpenConfig GNMI paths for LLDP state and BGP state. And so between turning up the point-to-point link and adding the BGP neighbor, I verified that the LLDP neighbor is correct. And then I also confirm after that BGP neighbor line is added that the BGP state moves to established. All right, so I wanted to go through a few lessons I learned in the process of building this hack. The first thing I want to call out is that there's just not a lot of documentation out there for using OpenConfig for configuration rather than telemetry. I don't know if it's that there's not a lot of people doing it or not a lot of people publishing it, but it was really hard to find examples of what I was trying to do. To combat that, though, one of the great things about OpenConfig models is that when you do a get on these paths, you get the config and the state all in the same request. And so I found the best pattern to use was to actually hand configure what I was trying to do on the device and then do a get against the path that I thought contained that piece of configuration and then build my request that way. And that actually ended up being really straightforward once I got a hang of that pattern. The other thing I want to call out is that if you're looking at OpenConfig to be purely vendor agnostic, I think you're going to be a little bit disappointed. I found that even the kind of simple set of configuration I was trying to do for this lab was not able to be done without adding in Arista augments. Specifically, when configuring an IP on an interface, I had to include the Arista augment for address type. And this augment makes total sense. You know, on Arista, you can have a primary or secondary IP configured on an interface, and the IP Yang model just didn't cover that. And so they needed this augment in order to differentiate. So I'm not really saying that as a value judgment, like this isn't me saying Arista did it wrong or OpenConfig did it wrong. I think that if you're going to use OpenConfig for configuration automation, you need to go in with the expectation that you're going to have to use augments. You're not going to be purely vendor agnostic, but you're going to be able to model quite a bit. And so I would highly recommend whatever you're using as your source of truth to also track what vendor you're applying the configuration to, so you know exactly which augments to inject. So obviously this is just a 2-day hack. It's pretty rough, but I have lots of ideas on how to grow it. And so just a few things I wanted to call out. It would be really cool to add in some APIs to surface some of that state data that I talked about before. For example, that LLDP and BGP data that I used for verification, it would be really neat to just be able to query an API and see the actual neighbors and BGP state and all that stuff. The other thing I was able to do, because this was a lab environment, was that all of those API calls were synchronous. So you submitted it, all the changes happened, and then the API didn't return success until the changes had gone all the way through. This works great for a lab where everything's directly connected, there's no latency and there's no wait. In practice, that doesn't work. You're going to want to implement some asynchronous task queues. You're going to have your API start a task, return a reference to that task, and then monitor that task through the lifecycle. Overkill for this hack, but something that would definitely be necessary in a production system. I was really hoping to get to the point of using GNOI to do some operational tests, and unfortunately I just didn't have time. One key place I was thinking of doing that was when I brought up the IPs on the point-to-point link. It would have been cool to do some ping tests across that point-to-point link to make sure there was no loss or anything like that. And obviously, there's a lot of use cases this can be extended to. I covered 3 very basic operational tasks, but there's a lot of room for growth on that front. The final thing I want to call out is that I didn't ever figure out how to properly incorporate augments in, like that REST augment that I mentioned before, using PyAngBind. So I have a really awful hack where I dump the JSON produced by PyAngBind and then load it up into a dictionary and then inject the augment in the right spot. If anybody has a lot of experience with PyAngBind, has done, used these augments before and knows the proper way to build those in, I would love to hear it. I imagine there's quite a bit that I did wrong just from not knowing OpenFig, not being familiar with it. And so I'm really hoping some people take a look at the code and shoot me some feedback. And so with that, that's my presentation. I've got the GitHub link here as well as my contact info. Please, if you have some time, if this is something you're familiar with, please rip apart my code. Tell me all the things I did wrong. I would love to hear what the kind of right way for interacting with this is. And then if you have questions or are trying to kind of build this lab on your own or having trouble, feel free to reach out to me and I'll walk you through it. Thank you.
Hi, everyone, and welcome to NANOG 81 Hackathon. And I am part of Team Telemetry, which includes Barry Jones-Cook, Jose Montero-Martin, Nate Sales, Pete Vikowski, and myself, Tony Anikalombo. And the theme has been configuration modeling. And configuration modeling really speaks to the heart of network automation, which can be great to automate configuration management in an automated manner. And of course, with it is the possibility of also automating errors. So care is always taken into making sure that we can improve on efficiency and reducing human error. A typical toolbox in this environment would have our development, test, and production environments as the base, and would have a network virtualization platform over which we would, or bare metal, and over that would have our network devices, which we could represent in the form of a YANG data model, and we would interface with that either using REST APIs or gRPC. For the sake of this project, we use gRPC, and as our team's name suggests, we focused on telemetry. And the use of build service and distributed source control is essential when we have multiple members of a team working together. And this is what our environment typically looks like, where we use Git for version control, Ansible for infrastructure as code. We had our dev environment running in Vagrant, and we used the Git repository for the source control. We had a network simulation that we used in the cloud on Amazon AWS, and there was some coding that was done in order to do a bit of testing, but we didn't focus much on that. And of course, for our chat ops, we had some Slack that we used. And Ansible was the main tool that we use for configuration automation. And as you know, Ansible is an agentless SSH-based open source automation tool. And in essence, it contains configuration management that we use to deploy our configuration to the network. And I'm going to hand over to Barry to run you through the rest of our presentation.
Thank you, Tony. Our team goals with this hackathon project were to start with a Vagrant environment that Tony had done some extensive work on before, and use Ansible within that environment to deploy Cisco CSR 1000V routers and hosts as AWS EC2 instances. We then wanted to create virtual private cloud subnets, VPC subnets, and ENIs, elastic network interfaces, and attach them to the instances. This allows you to create more interfaces on the virtual routers. Then we wanted to configure IP addresses, ping across, or use iPerf to generate traffic, and then stream telemetry from the routers using gRPC. Then on another host, we wanted to build GNMI gateway and subscribe to the telemetry stream. Our lab design looked like this. We had 2 CSR routers. We named them CSR0 and CSR1, and 2 hosts. And then we ended up actually building GNMI gateway on Jose's machine in Spain. So that is actually not in the virtual lab environment, but it was successful anyway. With that design in mind, I'm going to switch to the EC2 management console. And you can see here, this was a previous run where we renamed them manually. And this is the run that just finished. And the T2 mediums are the CSR routers. And the T2 micros are the 2 hosts. And then the GNMI gateway host is in Spain on Jose's box. And Nate is going to talk about the Ansible playbook that we created to run these. Thanks, Nate.
Cool. So this is our Ansible playbook that we are using to automate the creation and management of these routers and hosts. So at the top, we're going to start by declaring some variables, and these are defined in a single config file. And these contain things like secrets for your AWS credentials and things that would be different from deployment to deployment. So if you want to spin this up yourself, it's just one file to modify that can contain all the unique config for your situation. Going down, we're first going to configure the network topology with some AWS calls. This is going to talk to the AWS servers to set up these subnets and interfaces for the topology itself. Going down a little bit more, starting at line 34, I'm going to initialize some of those CSR 1000B routers. These are running in EC2. And then we're also going to attach those to the host and spine subnets so that they can communicate with all nodes in the network. Starting at line 48, we're going to create some T2 micro Linux boxes. These are just ping and iPerf hosts, just small machines that hang off of each router, which can then send some traffic between each other. And that's the traffic that we're looking to monitor with GNMI. At line 62, we are creating those spine interfaces, and then later attaching them to the instances, which allow us to peer between our 2 CSR 1000Vs. Finishing up the playbook, we are just doing some miscellaneous tasks, waiting for SSH to come up, and then sorting out all of the SSH host keys and fingerprints. In this case, it's just a lab, so we're ignoring any host fingerprints. There's no user interaction whatsoever. Of course, if this were a production system, we would ping those fingerprints, but this is just a lab. And then we have our second step here, which starts at line 105. And this is actually going to log into the Cisco routers and issue some CLI commands. First, just showing version and show interface description, just to give us a preliminary kind of just status of that we actually have 2 routers operational. We're also going to set system host name, so we can see which is which. And then going down line 134, we're going to import the SSH public keys so we can each log in to those routers and have a lab that's all totally ready to go and can just be logged into remotely for the rest of the configuration.
All right, and this shows the running config with the telemetry information that was created on the Cisco CSR 1000V. You can see that we've added a couple subscriptions for gRPC, but we're trying to do GNMI here. We can see that we've got a couple subscriptions in the detail, and the subscriptions are working. Working is a little keyword here. What we learned is that while certain devices do support GNMI and other devices do support gRPC based on the version of operating system that they have, not every device is created equal. The last thing we tried to do was we tried to enable GNMI Yang on a Cisco CSR 1000V, and we found out that it doesn't really run. It doesn't work, not yet at least. So what have we learned from this? Using the cloud does make testing of network technologies way faster and way easier to deploy with. It's really nice to spin something up really quickly, not have this big, expensive router or switch behind you, creating a lot of heat, costing a lot of money, and generating a lot of noise. It's faster and easier to test with when you're mocking things up. And having playbooks to both create and destroy technologies and topologies allows you to do things really, really quickly. If you've got a bug or you're trying to iterate through things, it makes life way easier. To continue, our future goals are to work on evolving the playbooks so that we can be vendor agnostic, meaning any device that we want to look at or play with for GNMI or anything else, we can just kind of plug in. It's no big deal. We want to finish automating our iPerf configuration of the host so that we can make sure that all the packets are flowing end to end as we want, and we can actually test telemetry that way. And we want to finish working on the GNMI gateway utilization for streaming and visualization. And with that, we want to thank you for allowing us to present here.
Thank you to our presenters and to all of our participants. I'd also like to thank the other hackathon organizers, Aaron Atash, Kat Gorinsky, Chris Woodfield, Jeff Bartig, and Valerie Whitkop. We're about to begin planning our next hackathon, and we're looking for participants, mentors, and sponsors. To help us in our planning, please fill out your surveys and let us know what you think about the hackathon format and themes. Please be on the lookout for updates, and we can't wait to see you in June.